Hey everybody, here's part one of what may include a part two someday, but this is just going to be the basics. So if you know your mod math already, you may want to skip this one. But here we go. For people that don't know mod math or what a mod inverse is, there is, first of all, let's take a look here. There's a regular inverse, right? This is called a multiplicative inverse. And so you just see that normally as like x to the negative 1 equals 1 over x. The inverse relationship comes in where if you multiply them by each other, you get 1 as a result. That defines an inverse. So it's really that simple. Math is largely just by definition, things are the way they are. So there's not really any logic behind it beyond that relationship right there. If you multiply a number times its inverse, you get 1. Typically that leads you to reciprocals, in fractions like this, but not always. Okay, let's take a look at the next slide. So you know how to use modular math already because you use a clock, and so you think in terms of mod 12 all the time, you just don't know it. So if you think of like military time, like 1700 is 5 o'clock, and you know that just off the top of your head, you should. 1900 would be 7 o'clock, right? Like 2200 would be 10 o'clock, because you're subtracting 12 to get the AM PM time that we're used to thinking of. So modular math is really just based on this. So this is a little bit dry, so just bear with this slide for a moment. But if you consider numbers that would satisfy this formula here, where you have a minus b, and let's assume that a is bigger than b, so we get a positive result here, just to keep it simple. But if you subtract b from a, then the result is going to be some multiple of m. And so you would see that only certain numbers fit that pattern. Like here's a couple of examples using mod 12. 19 minus 7 is 1 times 12, right? It fits the pattern of a minus b equals k times m. Same thing with 37 and 13, and these would be familiar times, right? If I said 1900, 1900, 700. If I said meet me somewhere in 37 hours, pretty obviously that's 1.5 days plus 1 hour, because of the way that we can mod things by 12. So anyways, let's move on to the next slide here. I would point out to the modular arithmetics page on Wikipedia being pretty useful if you ever want to look at this more. Now let's talk more about what mods are based on. Mods are based on cycles on a number line, basically. So if I'm looking at, if I divide 2 by 5, what do I get? I get 0, right? But then I get a remainder of 2, and that 2 is the mod part. So if I said 2 mod 5, I'm going to come up with with the answer of 2. But if I said 7 mod 5, if I did 7 mod 5, I get the same answer of 2. And if I did 12 mod 5, I'd get the same answer of 2, right? Because each of those, if you look at these markings of every 5 points as making a cycle, then every distance from one of those points is what your mod is going to be. So what you can see here is that numbers are congruent. This is introducing this kind of funny equal symbol here. That's not a regular equal symbol right there. What that means is like 17 is right here, for example, and that's 2 away from a multiple of 5. And then 12 is right here, and that's also 2 away from a multiple of 5. So that's what's saying 17 is congruent to 12 mod 5. And notice we're using these parentheses here. Let's take a look at the next slide. Let's look at congruence a little more too. I'm introducing the concept of congruence in the last slide. And so you've seen this before in geometry, like these two triangles here, which I stole from Wikipedia, are congruent. They're like rotated differently, they're in different locations, but they pretty clearly have the same length and angles of the length of the sides and the size of the angles. So that's and you think of I guess I make the example here that you think of mod math in terms of angles and geometry on a clock, right? Because we can just glance at a clock. At least those of us that grew up without digital clocks can just glance at a clock and know what time it is based on the angle of the arm. And so whether it's 1900 or 700, that arm's going to be at the same angle, and so we recognize that as the multiples. Okay, so now there's this thing called the modular multiplicative inverse that comes along, and you've seen this congruent symbol here that I've shown you. So the symbol is basically saying what I was talking about before. It's always going to be presented as A is congruent to X, mod N. I mean, A and X can always be different variables here. Could be X and Y, could be A and B. N is typically used here. And notice that you may see this with the little tilde instead over the double equals, but we're looking at a triple equals here. We're going to use that symbol for congruence. So sometimes the parentheses are missing. You have to watch certain assignments. I think I have a slide on it here, I forget. You have to watch certain assignments like R's and IAS that'll say something like 33 is congruent with 65 mod 32 without putting the parentheses in there, right? But the parentheses are really implied. And I've seen a lot of sources that omit the parentheses, and that's not good. It's kind of a lazy step. So let's talk about RSA just for a second here. We're almost on the last slide, so the video is almost over. So if you're impatient, just hang on just a little longer here. But let's say Alice and Bob, that's the classic names used in security. Let's say they want to share a message privately, and they want to send the encrypted message to be like not something huge compared to the original message. That's not something that's often brought up in RSA, but it's a function of the modular math that RSA is using. You basically are taking a message, and you'll see in the next slide, you're taking it to a much higher power, but you're in the long run not increasing the message length by anything. You might take something to the 17th power, some huge, large number that represents a message, and then square that, or cube that, or take that to the, like I said, the 17th power. You never know, and you would think that would be a just hugely much longer number. But it won't be because of modular math. Because of those cycles, you can always divide it by some mod, n, in our case of RSA, we'll see on the next slide, and then you'll just get like a manageable number that's between 0 and n minus 1. All right, let's take a high-level view just for a second before we dive into what P and Q are and what n is. Remember that we're dealing with RSA here. That's what we're building up to. We're building up to building a message that can be encrypted so that nobody can eavesdrop on it. It's the typical thing with Alice and Bob, and then there's Eve, the eavesdropper, trying to read the message, and we're trying to make sure that only the sender and the recipient would know the contents of the message. So, we're talking about keeping these messages a manageable length in part because of using mod n. Well, what is this n? So the n is just it's just made up. It's not like some magical number or anything like that, but it is a composite number, meaning that it has factors. It's not prime. N itself is not prime, but it is made up of the multiplication of these two factors, p and q. So if you look at it here, n equals p times q, which for the people learning math, sometimes you'll see things just directly next to each other like that. Otherwise, you could have like a multiplication sign in between the two, or a dot to indicate multiplication in that context. But you can also just see it like this with nothing in between. Anyways, so n is p times q. What are p and q? Those are prime numbers. Those are pretty large numbers, and then they multiply together to make a length of n that gives us a key of a certain length. So what is totient n? Totient n is going to come up in the discussion in future videos. We're just going to introduce it at this point and not really dig too much into it. But the totient of n is from this Euler's totient function. That's phi of n, and what that is p minus 1 times q minus 1. Again, you can see two quantities put next to each other without any dot or multiplication sign, and it's just inferred that you multiply those two together. Okay, so we're just introducing P and Q here. Future videos will look into the utility of them. So finally, last slide, hooray, consider these RSA algorithms. This is how you actually make a encrypted message from a plain text message. So the C is going to always represent your encrypted message, and that's congruent to m to the e power mod n, right? So we've talked about n, we haven't talked about e yet. I guess it really deserves its own slide, but in short, e is just the public exponent that you use to exponentiate the message. Let's take a look at e for a minute. E is a number by the RFC. The RFCs are the official documents that define the internet structure, and things like RSA have RFCs as well. So the RFC says that E should be any number between 3 and n minus 1 that's odd. Typically people use 65, 537. You should use something large like that in practice. 65, 537 or larger, up to n minus 1. But in academic circles, we always use like 3, or I mentioned 17. I mean some small odd number. So what else would I have to say about this? So to encrypt a message, it's right there. You just take m to the e power and then mod n it, and that gives you the encrypted message. Even though that's congruent, it also happens to work out that the equals sign would work there too, right? This is actually a function for generating an encrypted message. And then if you have the decrypted, or if you have the encrypted message down here, and you have C, then if you take that to the D power, then take that mod n, you're going to get the message back. So like the slide shows here, we're encrypting the public key, we're encrypting the integer here, m. Remember, these messages are all represented as integers at the end of the day. And then you go to encrypt it by taking it to the e power, and the public key is the combination, is this couplet of n and e. N is your n that you've chosen by putting together from P and Q, and then E is going to be your public exponent that you choose. So then when you go to decrypt it, there's a private key D, and you take the encrypted message C to the D power, your private key, and then you know the public key because you're the person that made the public key too. And so you can mod N and get the encrypted message back. And what did I say down here? When we raise m to the e power, consider that the message resulting will likely be larger than n. So yeah, I'm kind of going on and on about this, about how, keep in mind how this keeps all the messages short. It keeps the information from just blowing up on you as you exponentiate it. Alright, so it's time to wrap up the video. Thanks for watching so far, and let me try to summarize here, and maybe give you a little bit of practical information to use. So you might be watching this information because you have a programming assignment, and so I guess I'm not giving too much away if I just say, there are built-in Python functions, and one of them is POW, and so you should take a look at that one when you're looking at exponentiating something like this, and also for using a modulus. Look at the Python POW function. Since 3.8, it's been able to do some pretty interesting things. So that's a tip for that. And I guess I would just say in closing, there may be a future video or may not, I'm not sure yet. If there is, it's going to be more relevant maybe to graduate algorithms and talk about some of the tips and tricks for dealing with exponents and RSA in that class. So if I make that, we'll see you again. If not, thanks for watching, and I hope you all have a great day.